This will be our last presentation today, with Andrey Belenko is going to talk about dangling DNS records. And without stealing your thunder, let me just hand the floor over to you. Thank you very much, Timur. Indeed, my plan is to discuss DNS records with you. In particular, dangling DNS records, that is, pointing to non-existing resources. Actually, translation of the word dangling into Russian is a bitch, so I will simply call them dangling, simply to save time. Let me start by telling you briefly about what I do. I'm currently leading a small team at Microsoft. Before that, I was responsible for various security topics, primarily in various startups. I was in charge of IaaS, clouds, and password recovery. My mandatory disclaimer is that I'm making this presentation in my personal capacity. I'm not speaking for my employers, past or present. Please allow me to start by reminding you how DNS works and what it does. DNS is effectively a system that matches human readable and rememberable server names to IP addresses that are actually used by computers. When you enter a domain name in the browser address field, the first thing the browser will do is to actually match it to an IP address. In order to do that, the browser will actually need to contact a DNS server. Actually, it probably should be called a recursive resolver, but most people around the world call it simply a DNS server. So the recursive resolver returns a response containing one or numerous IP addresses related to a particular domain name. Actually, there is more happening under the hood. In particular, the important question is how does a recursive server actually know what the right answer should be? And this is something that I would love to address, but a bit later. In the meanwhile, let's look at DNS record types available. I am primarily interested in record type A, and this is a simple juxtaposition of a name to an IP address, and a single name can be associated with numerous type A records. Another record type is CNAME. It's actually a sort of an alias. So a single domain name will be associated with another domain name, and a DNS server will return the CNAME instead of the one that he initially requested. Now, let's try to identify what a dangling DNS record is. A dangling DNS record obviously should, as the name suggests, should point to a non-existing resource. So imagine that a user has decided to create a website. So this user turns to a hosting service, creates a cool website there. Usually platforms like this invite you to use either a random name or a very long name which is hard to read. They usually tend to be third or fourth tier names. Something like I have here in the slide, coolwebsite.longgenericname.net. And the user may be happy with his website, but the problem is that nobody can remember names like this. And then the user will learn that he can actually register, well, not that much a random second-tier domain name. And that way, when a user enters my.website.com, they will be able to actually be redirected to the content which is currently stored in coolwebsite.longgenericname.net. So everybody should be happy. And then a user may decide that he's no longer interested in the website and he has the site deleted by the ISP, or rather by the web provider, site provider. But he actually doesn't care what happens to the DNS record, and the DNS record may persist. It does happen quite often. So it may happen that mywebsite.com will continue pointing to an asset that no longer exists, and this is what we call a dangling DNS record. Well, in practice, it may lead to a domain hijacking. Finding such dangling DNS records is possible. Once they have been found, there will be people who will want to register the same name that was previously used by another user but has been freed by that time. And this is how they're actually going to capture this domain name. And this way, when a user types in my.website.com, will actually be directed to the website of the attacker. Now, what's bad about it? Well, this way, the attacker hijacks all the trust, all the goodwill associated with the name of the domain. Well, in our case, that's the goodwill associated with my.website.com. And this goodwill can come in two varieties. One is the trust of a particular user. For example, when you enter a website called something yandex.ru or something microsoft.com, users usually will consider it quite reasonable to trust whatever they are seeing, because these are established, solid corporations who should know better. So hijacking domains like this could actually be great for phishing or malware distribution, and actually other bad activities as well. But this is just part of the problem. What is actually even more important is machine trust. So there will be systems that will trust this website, and here I can give you a couple of examples. One deals with the cookies, HTTP cookies. They may differ in their scope, and in particular their scope may include subdomains. And I actually have a slide on that, several slides later, that will show it in practice. But in a nutshell, a scenario like this is where you actually get access to subdomain cookies, which may contain sensitive information. A pretty widespread pattern is such that the client will have some limitation or constraint lists regarding where certification or authentication tokens can actually be sent. There may be a filter built in that will say that we'll only attach authentication tokens bound for, say, Microsoft.com. So if you take over a subdomain in a list like this, it will be easier, very easy actually, for the attacker to get access to the authorization and authentication tokens. Similar case with OAuth redirect URLs. What may happen is that the domain in a redirect URL has been taken over. Well, then the attacker can impersonate the users and intercept tokens. And finally, other scenarios include firewall and CSP bypasses. It's a common practice for vendors to publish lists of IP addresses and domain names that must be allowed in the firewalls for systems to work. This is a pretty common situation for telecom systems like Skype for Business, Zoom, or Microsoft Teams. So if you capture a subdomain like this, you will find it very easy to bypass a firewall. Let's look now at several recent cases. We will consider 3 cases in particular. All of them deal with Microsoft. And let me stress here, let me point out that Microsoft obviously is not the only company being hit by it. I just decided to focus on Microsoft because A, I work for the company, and B, I know these cases very well because I've had to address them. So one of these cases is associated with Azure, and it took place about a year ago. And it is actually a OAuth redirect URL. So it was actually pointing to a recently freed up Azure resource name. So CyberArk registered a resource on Azure, and this is how they got a web server. And the identity provider, that is Azure Active Directory, would send authentication tokens for the users, which means that if users browse the website of the attacker was able to get their access tokens. Or a variant on this attack could be, for example, could simply involve an iframe replacing a visit to the website. And the effect is such that a user either clicks a link or visits a malicious website, and then the user's token is grabbed by the attacker. Another recent case that I have been exposed to was that of Microsoft Teams and cookies. So we have an authentication cookie which has a scope for Teams at Microsoft.com, which means that browser will find it easy to redirect it to any subdomain in Teams. So what the attackers did was to find 2 dangling subdomains. They register them in their name, and this is how they got access to domains that browsers felt quite good about sending authentication cookies to. In order to trigger cookies to be sent, they would send messages to Microsoft Teams with a link to an image. And this picture would lead to their website, or rather the domain that they took over. And that was it, really. I'm not giving you all the details. It was a bit more complicated than that. There was another level of a redirect. Simply because Teams clients would not open pictures with links. So they use another step to get there, but this is of little importance for our purposes. Actually, this has been found by the same researcher as the previous Azure case. And the effect here was that you could send a message to a user, and the client would automatically request this picture in the background. And together with this request, authentication cookies would be captured. So you didn't even have to click any link. All you had to do was simply to open the message. And another recent case dealing with account takeover in Azure DevOps. So for those who probably don't remember it, Azure DevOps contains like, well, it's a sort of a GitHub for the large companies. It's a similar case. So we had an auth redirect URL leading to visualstudio.com. So researchers actually found a dangling record leading to one of the subdomains of visualstudio.com. And initially they didn't think it was good for exploitation. But then they discovered there was a redirect URL which contained a wildcard, meaning that it was indeed good for exploitation. And the effect was similar to what we discussed in case 1. A user browsing the website being controlled by the attacker would have his tokens compromised. Unlike case 1, the big difference here is that the attacker is effectively controlling a higher grade domain name, that is visualstudio.com. Chances, that users would trust a second-tier domain like this are actually higher than a subdomain. Obviously, Microsoft is not the only company exposed to that. It's just that there is more news about Microsoft simply because it's such a large company. But there is another company that was, quite open and public about a similar issue, was Starbucks. In February, one of their security experts made a pretty interesting speech at RSA conference. He covered lots of interesting aspects. He explained, for example, that their domains are hijacked in a matter of minutes once after they've been freed, which shows the amount of attention that bug hunters have for issues like this. Unlike many other companies, Starbucks is actually paying for cases like this in the bug bounty program. Actually, many other companies don't do that. Now let's look at a classification of dangling records. Dangling a record is probably the simplest class. It happens when there is an A record in a DNS which points to an address not being used, and the resources associated with it have been deprovisioned and deleted. Well, I first heard about it back in 2015. Back then, one of the researchers created a page in his blog where in real time it was running on AWS. So the system would allocate, some capacity to it, would create a virtual machine. And then would do some local magic in order to check what kind of domain names would be pointing to this address. It was quite interesting, actually. Like, we have identified this particular address, and this name is pointing here. It was interesting. But I guess it became a bit too expensive, so this service is no longer functioning. I actually think it shows very clearly that IP address collisions, which may sound like a highly improbable occurrence because the namespace is so large, but in real life they do happen. Particularly if the objective here is not to mount a targeted persistent attack, but rather it's an opportunistic attack. When the attacker wants to, take over some company that commands some trust. Take, for example, AWS. If we study their elastic computing clouds. Roughly, it contains 2 million IP addresses. Well, their actually largest region is 16 million, and the smallest is 130,000, but the average will be 2 million. Please note, this is the total number of public IP addresses associated with a particular region, not just free addresses. At any point in time, a significant portion of this namespace will be used. So you can practice your theory of probability skills here and simply calculate how probable a collision may be if you know that a particular address is available. Well, the way I see it is that it is at least possible. Okay, next type of a dangling record is a dangling CNAME record. I actually think this one is the one that gets most exploited. And the case is as follows. It is actually similar to what we discussed before. When we looked at our notional case, so we have a DNS record, CNAME record pointing to a resource that is either not provisioned or unregistered or non-existent. Quite often, the name that a particular CNAME points to will exist in the so-called public suffix domain. What a public suffix domain is. This is a concept from the world of domains. And a public suffix is a domain where a user will be able to register a name. .ru, for example, is a public suffix domain. Anybody can do it. Same goes for .com. In our example with the website, the provider of website services or hosting service, and it's hosting, right? So in any case, that was also a public suffix domain. On GitHub, they actually have a list collecting names and addresses of all the providers that enable you to create public suffix domains. There are actually over 50 lines in this table. Well, take Azure, for example. Azure is there. It's just one of the lines, although Azure provides so many different services. Actually, some of these services are, in fact, providers of public suffix domains in their own right. Naturally, this problem is nothing but new. I don't think I'm telling you anything you don't know. For example, in 2016, there was a very good academic paper published on this subject, and I have all the links at the very end of my deck. If you read security blogs, or if you simply follow leading bug hunters, or what you analyze being the blue team, will show that this is actually the most popular type of dangling records. The majority of people will be interested in those, and it is pretty easy to identify them. Another characteristic of dangling CNAME records is that they're easier to find compared to some other types. One of the expectations, the ones that I have, is that by 2020 this problem should have been resolved. But as I was preparing for this presentation, I decided to test this hypothesis. I conducted a micro-analysis of my own. I took a list of publicly available DNS records. It contains roughly 200 million CNAME records. 200 million is a lot, and much of it is bullshit. So I decided to focus on the top 50,000 domains. I used a Tranco list. It is sort of like Alexa list. You know, had I been using Alexa top 50K, it would be similar. Well, next, I actually filtered them even more. I decided to keep only the CNAME records that would be pointing to 4 very popular cloud services, not providers. Let me stress this difference here. One was the regular compute, regular virtual machine. You know, when you provision them, you know, they will get a domain name, publicly available. Another one is a service for provisioning websites. Third one is a load balancer. And the fourth one is a gateway. So when you provision resources, you'll get domain names, and you should be able to actually choose resource names. After I applied this filter, only 110,000 CNAME records were left, out of which 1,400 turned to be ripe for the taking, turned to be dangling, which came as a shock to me. Because like I previously said, it is a well-known issue. And I think that risks are pretty well known. And I decided to focus my analysis on the big guys. So it should be even worse for the smaller ones. So these are the results I found. 2 airlines, 1 airport, several major software vendors, major auto manufacturer, government offices of 5 countries, several major universities. So all these institutions had dangling records in their domains. And all of these domains are ripe for the taking. You know, they just sit there waiting to be hijacked. So a person or a group that takes MOVA will have full control over the domain, but also will have control over the trust that users put in the institution. And to an extent, you know, they will become a part, you can argue a bad part, of a company they will start to impersonate. So, although this problem has been around for quite some time, dangling CNAME records are still quite common. The good news is that if you start using a CNAME record, it enables access to a single domain only, or maybe a subdomain name. It is still an important risk to consider, but it could have been much worse. You know, actually, in many cases, if you control the domain, it means that you control the server running there. So you can install, you can put up HTTP validation, you can issue TLS certificates. And actually, you know, most authorities will issue those certificates to you. Like I said, a dangling CNAME enables you to capture a single domain. But how about taking over a whole subzone? Even that is important. Even that is possible if we find a dangling NS record. And this is a great opportunity for us to return to our exploration of how DNS works. Remember the magic cloud I had. So when a recursive resolver gets a request for resolving a particular name, in fact, in most cases, it will not know the answer. It will not know what the right IP address is, but it knows how to find it. It is done pretty quickly, although several stages are involved. First, it will go to the so-called root zone. So it will request a name, or rather an IP for a name. Actually, the name will be broken down. Like www.contosa.com will be broken into 3 parts. So root zone is what actually comes after the last dot, right? So it starts from the end. It will address service responsible for different root zones, asking them if they know the right answer. So the first request will be sent to one of the root name servers, and their list is actually hard-coded. Most resolvers have it hard-coded in, in the source code or in their config files. So the name server will compare the name to the IP list that they have. We'll check if it sits in the .com area or not. It will say, well, I actually don't know the right answer to your question in full, but I know what scope for .com is. And this is what we call referral here. So the root name server will send a referral to name server. Our recursive resolver will get this response, and it will actually send a query to zone.com requesting the IP address for www.contosa.com. And the name server doesn't have the answer, but it does know which name server is responsible for contosa.com. So it will return a similar referral saying that contosa.com zone is managed by ns1.contosa.com. Then our recursive resolver will turn to name server 1, that's ns1.contosa.com, and then, bingo, it will have the answer. Because this one is the authoritative name server for this particular zone. It does know the IP address. Because this www entry belongs to its scope. So it returns the right response. Now you may tell me, come on, Google and other search engines or DNS providers actually take less than 50 milliseconds to perform all these operations. How come? It's impossible to do it in less than 50 milliseconds, and you're absolutely right. Actually, the main reason why public recursive resolvers work so fast, this is because they use caching. So the responses they get from root servers and high-level name servers are obviously stored in the cache. So all these delegations and allocation of responsibilities are managed by NSs. So for example, here we have sub.contosa.com, and this is an NS record type. What it means is that sub.contosa.com zone is delegated to a particular name server. It means that all the records above it will be managed by this particular server. I think you know where I'm leading. At Dangling, NS record will be pointing to a name server which doesn't know much about the zone that has been delegated to it. It can be exploitable when a zone name server belongs to a shared or a managed DNS service. In the recent years, now that cloud has entered so many parts of our lives, cloud DNS therefore has become such a commodity. Pretty much anybody can create a zone now. Amazon, Azure, Google have got their own cloud DNSs. However, there are also lots and lots of other providers who offer shared or managed DNS services. Very often, these are the same companies that specialize in web hosting, or domain registration. You may have noticed that I have struck Cloudflare out. I will explain it in more detail later. I have not been able to abuse Cloudflare servers. Apparently, they are applying a certain logic which will limit such exploitation. I'm not saying it's impossible to exploit them, but it's certainly much more difficult than with the other providers. So here we're looking at sub.contasa.com. But the situation would be the same for contasa.com per se, because top-level DNS zone is no different from a sub-level one. If we see a dangling NS record, that is an NS record pointing, to a server that doesn't know about the area has been delegated, well, you know how it works. The next question is sort of obvious. How prevalent is this issue? I applied the same methodology. I took the list of publicly available DNS records. It contains something like 550 million NS records. Similarly, I filtered out everything except the top 50K domains, and this gave me something like 5 million NS records. I decided to keep only those that pointed to 7 most common cloud or managed DNSs. Guys, Amazon, Azure, NS1, Google, Alcan Electric, and something else. I don't really remember what it was. In the shortlist, I had 1.3 million NS records. That is roughly 450,000 zones or domains. How come such a difference between records, or number of records and number of domains? In order to increase resilience, several different name servers will be used for the same domain. And each of them will therefore constitute a separate NS record. A typical situation in practice is such that, say, subcontasa.com will have several NS records and therefore several different name servers. This is just a matter of redundancy or resilience. If one of the name servers goes bad for any reason, the system will stay functional or operational. What this means is that out of 450,000 zones, roughly 140 zones were available for the taking. I guess I got my percentages wrong here, and I offer my apologies for that. However, even that number is not good. It is not a negligible amount of zones. And again, note that I did very aggressive filtration on my list. I only focused on the largest corporations, most popular websites, the most sophisticated DNS providers. So 140 may look like a small number, but you have to multiply it several times. to get a more representative picture for the bigger portion of the market. Who did we find there? A cloud monitoring company. Pretty much all the categories are there. A major virtualization vendor. Major software vendors. A movie studio. A car manufacturer. I was really surprised to see an NIC there. Because an NIC should know better. These guys are responsible for regional internet. Naturally, there were also ISPs, major IT companies, and so on. 140 is actually a lot. So it covered an impressive breadth, or consisted of lots of diverse institutions. Another interesting aspect of dangling NS records is that if you exploit them, you can actually get access to limited top-tier zones. In particular, I was interested in the .iro zone. Actually, in order to register a name there, you have to belong in the world of aviation. There is a certain verification procedure you need to go through. I guess you can actually dupe this procedure, and probably some of the domain names can be bought in the black market. But my question was different. I was wondering if it was difficult to hijack a second-tier zone in the .iro domain. My methodology was simple. One can get access to all the entries in this zone, which I did. And the full list contains about 33,000 records, which should roughly correspond to about 15,000 domains. Over 600 zones, or over 600 domains, were dangling. Which means, they pointed to NS servers that didn't know about them, and 25 zones were clearly hijackable. That is, they pointed at some managed DNSs where it would be extremely easy to hijack them. I am absolutely certain that significantly more than 25 zones are hijackable. It's just that checking it would require registration in Godzillion of hosting service providers and ISPs and hosting providers. That's right. But even 25 zones is not negligible. So coming back to the issue of trust, the official rule is that you have to belong to the world of aviation to get registered in this zone. So the expectation would be that if you have access to this zone, well, then you got a right to belong there. It sounds like you've gone through the validation and verification process. A similar experiment I conducted with slightly different data. I am referring to the .gov and .gov.xy domains. Well, as the name suggests, they should be governmental institutions. Unfortunately, I was not able to get access to the zone file. I don't think it's public, actually. So I had to use publicly available data. So I used, for example, data coming from various online scans. I was able to find roughly 97,000 records. I don't remember how many zones were there, but in any case, roughly 200 zones were dangling, and about 10 were clearly hijackable. I'm absolutely certain that more can be identified if we actually spend more time exploring it. On the one hand, we need to go deeper into subdomain enumeration, because these are public records. This is not the full list of all zones or subzones. And secondly, in the zones, there is actually an interesting sort of distribution in terms of what is being used for hosting purposes. There are several companies providing services. These are managed DNS services. But they don't come from the list of popular service providers we all know. So let me summarize. Dangling DNS records are less common than dangling CNAME records, but this doesn't mean they don't exist, and finding them is not that difficult. At the same time, they are substantially more powerful than CNAME or A records that are dangling. For example, you can take over a dangling DNS record, then you can add CA records, or you can set up an email service there. A CAA record, for example, will enable you to publish certificates on the parent domain. Very briefly, we are going to cover another type of DNS records, that's MX. MX record types enable you to configure mail delivery rules. For example, a letter sent to mail.contasa.com will effectively go to mx.something server. So a dangling MX record points to a mail server that doesn't exist or doesn't know about the zone or is not configured for receiving mail for this domain, which means it can be exploitable. If it is a managed server or a shared server, and actually the fun thing is that it may allow an attacker to receive email on the website he doesn't own or she doesn't own. I have not done any analysis in this respect, but if you are interested, please follow up. This should be an interesting piece of homework or an interesting venue for exploration. As regards potential mitigations, I am proposing two ways to do it. On the blue team side, the list of things we can do in order to avoid it is here. If alias records are supported by a DNS provider, use them. What is a DNS? What is an alias type record? An alias record will automatically control the time of life or the life cycle of a DNS record. So, for example, if it is pointing to a cloud resource, say a VM, usually provisioned by the same provider. So when you delete this virtual machine, the DNS record will also be deleted. This way, you're guaranteed to never have the situation that you will have a dangling record. Well, because the pointer will be removed together with the record. This, however, This, however, applies to situations when all the services are provided by the same company. But it's a matter of topology, I guess. Now, if you have an issue with dangling CNAME records, you can also consider how you can make exploitation more difficult. For instance, you can add your domain to HSTS preload. This means that an attacker, once he has taken over your domain, will have to obtain a TLS certificate. If the domain is in the or on the HSTS preload list, it means that browsers will not contact this subdomain for resolution. They will instead go one level higher. And if the attacker has to obtain a TLS certificate, well, you will learn about it the moment he or she has done it, as long as you monitor certificate transparency logs. You will notice that somebody has obtained a TLS certificate for your domain, and chances are you will realize that wasn't you. For example, if you're using a particular certification authority and you pay money for it, and somebody got, a different TLS certificate from a different CA. Similar mitigation will involve adding a CAA record to your root domain. This will limit the CAs that can actually issue TLS certificates for your domains. So if you have contracts, or if you simply know that you always get your certificates from the same vendor, you may simply make sure that the other CAs are simply not on the list. Combined with HSTS, this will be quite a powerful way of mitigation. I added DNSSEC here, although in practice it doesn't get used really, or doesn't work. Ideally, you should have a process for managing the lifecycle of DNS records. A process that actually works and that makes sure that you don't have dangling records. Unfortunately, in practice, companies taking up more than one room find it very difficult to organize and maintain a process like this. Particularly in the environment where everybody does DevOps, they do everything themselves, they deploy everything on their own. It is a challenging issue. Now the red team style mitigations are here. One of the effective ways to do it is to become an attacker. Simply to monitor all your domains, all your DNS zones, and the moment you identify something that's dangling, either take it over or do something else about it. In order for this to be effective, the red team must have decent visibility of what is available in the company. I guess most red teams have it, but I'm not entirely sure that it applies to everybody under any conditions. Actually, if the company is getting larger, if it becomes large enough to occupy multi-clouds, there will be issues in this department. Interestingly, such a solution can cause outages or can intervene with the functioning of the system. I had a case like this. When a domain was taken over, anybody could do that, but that was me. And it resulted in a 6-hour-long outage on a particular element of the infrastructure. So one should be careful here. Also remember the costs. This is not cheap at all. Again, it all depends on the company's size, but the costs associated with such a solution can easily grow faster than you expect. Let me tell you again about Starbucks. A gentleman from Starbucks made this presentation at RSA conference earlier this year, where he explained that they have this system which does DNS zone scanning every several minutes, and whenever they identify something dangling, they react real quick. They may, terminate the records or take the zone over. For service providers, the mitigations we can propose are as follows. On the CNAME side, you can disallow users from choosing names. For example, you can simply use system-generated domain names. If you do have custom domain names or vanity names, you gotta use structure validations, which means that you will need to check the way that mapping is being done. Like in my earlier example, we would benefit from having a more robust validation of ownership of my.website.com. In any case, service providers need to up their game in terms of validating domain name ownership. Many DNS providers don't do any validation at all. They seem to be acting on the assumption that if you are adding a name zone and you have the NS name record in the parent zone, everything is fine. But I think my talk has already shown this is certainly not true. And Yandex, I think, is the only company that is serious about validating this. Actually, they say, we want your email to be in the who is lists. Well, I'm not saying everybody should follow this example, but this does prove that some companies do it right. Now, for dangling NS records, what cloud providers or managed service providers can do, they can actually complicate for the attacker the process of getting where they want to be, getting to the correct name server. All managed service providers have several kind of partitions for name servers, several different pools actually. So when you create a zone, it will end up in one pool. With some providers, this decision is made randomly. In some cases, there is a deterministic rule for it. The more complicated this process is, the more difficult it is for an attacker to, connect to the right name server, the better it will be. My understanding is that when you create a cloud account with Oracle, no, it's actually different. With Oracle, you can only create a single zone with a certain name. With other providers, you can actually create as many as you have shards or partitions. And Cloudflare has got some magic as well. I'm not entirely sure how they do it, but so far I've not been able to get the name servers I wanted. This puts the lead on my presentation. My key conclusions, my key takeaways are such that dangling DNS records are still quite prevalent, and any company that has a non-trivial surface in terms of DNS, I think will have dangling DNS records. There is no single one-size-fits-all solution. But for companies of different sizes, there can be different solutions that can be proposed. And these are references to various resources. First one is a blog Next one, the third one is the RSA report from Starbucks I mentioned. And finally, the report I mentioned about DNS records. If you have any questions, I'm happy to take them, and please study the links at your leisure. How are we doing in terms of time? Well, this is actually the last presentation we have today, which means that we do have a couple of minutes for questions and potentially answers. We do have a question from one of the listeners. Can you please explain how an attacker, for example, will register a domain, say, in the Microsoft zone? Sure. I'll go to the very beginning of my presentation to make it clearer. This is actually what happened to Teams in this particular example I mentioned at the very beginning. So here you need to replace website.com with teams.microsoft.com. That was the configuration. So there was a name, something.teams.microsoft.com, that would point to a resource on Azure. Something.azure.net, for example. Then, the team that was responsible for this service on Azure, a Microsoft Teams team, discontinued, they deleted this Azure website because of some reason. Maybe they decided to change something, or they decided the server was no longer needed, but the record was still there. Something.teams.microsoft.com was still pointing to something.azure.net, but this resource on Azure no longer existed, which means that any user of Azure, with any subscription you have, can create an Azure website using the same name, something.azure.net. And this is it. End of story. This means that all requests, all queries pointing at something.teams.microsoft.com will be redirecting to the Azure website registered by an attacker. Okay, thank you. Another question. So you said that name randomization would be a good idea for service providers. Why not all service providers do that? It is difficult for me to comment on their behalf. Let me stress, however, that I'm not proposing randomization. Randomization itself is not the cure. What I'm saying is that these names should not be generated by humans. It can be a simple counter for all I know. This way, you will make sure that the same name will not be generated, will not be hogged, so to speak. I guess randomization will do the trick as well. I don't really know why providers don't do that. I guess they have their reasons for it. But I won't make guesses about the nature of these reasons. Last question. To what extent is it being used in real attacks? Have you seen it actually being used in real attacks involving, say, token capture or social engineering? I would love to answer this question, but I don't have the data to support any claim like this. Information on real attacks at Microsoft would be interesting, but what we can see in the bug bounty program, like these three examples, they're all 2020. And there are more. There are other reports of dangling domains. And these three examples are quite illustrative. It's just that, the researchers went the extra mile. They took some time to show how they could be exploited. Thank you very much for your time, Andrey.